Ladies and gentlemen, it's a pleasure for me to stay here. Last year I gave a similar lecture, but this day I have much less time than that time, so I worked to skip my voice. I hope not the most interesting ones, I could keep the good ones. Well, as we heard, laser research and cooperation with dental research can give good results, especially in the very quickly developing dental science. But in my lecture I would turn back a bit wider overview. How can we use lasers in dentistry? And let's start what I like to tell you. First of all, I have to tell you that I'm a physicist. I like to work with laser material interactions, and I will have some slides concerning this one. And my main question is, what do lasers with teeth? So tooth has a certain material, certain optical, mechanical, and thermal properties, and we want to do many things with teeth. The worst cases are the oral surgical cases, but there are also an increasing wish to have whiter teeth. Especially a good possibility to keep our teeth in a good condition, to preserve teeth material when we close the fissures, and later on, when we get older, we can have more sensitive teeth. There are many companies who deal with this problem. Also, toothpaste, you know probably the name of Sensodyne, and other companies as well. And I will think about root canal treatment. There is one application which is not here in this lecture, because the next lecturer, Dr. Marta Philip, she's a practitioner dentist working at Budapest, and she uses lasers herself, and I think she can give a first-hand information about how to drill teeth material with lasers. Therefore, I will just mention this topic. So I will tell some words about future possibilities before the summary. So this is a famous image in Szeged. Many places you see this hand. If you see my hand, it's similar. It is my hand, by the way. And what you see that when I have a diode laser, or better to say a diode laser pump neodymium laser, it is very similar size. We can just light a paper when we focus this light. So the laser emits a strong light. You can see in this image that just the scattering can be visible. This is the very first, one of the very first types of lasers, helium neon laser, and we excite the laser material, and with a resonator we can amplify this light to many times, and across the semi-transparent mirror this light leaves the resonator. I will give some boring definitions at the beginning, because they are important to understand the interactions with teeth material. So the first one is the power of the radiation. The definition is very easy. We have an amount of energy given in a given time, and energy divided by time gives the power. More important is the intensity. If I use a given power to a large surface, nothing will happen. Just if we want to say the power of the sunshine in normal daily light, so middays on the roof, the power on 1 square meter is 1 kilowatt. 1 kilowatt is a huge power. It is comparable to a washing machine, for example. And the sunlight does not do anything with our teeth or with our body. So it is a low power. So the definition of the current density or intensity, when we have the power, we have to divide it with the area where the interaction happens. This is a differential form, but when we want to calculate the average intensity, we measure the energy which came out from the laser and divide it with the time, and also divide with the area. So you see first an image with laser, and we can do this experiment with sunshine as well. So we can light a paper, a black paper with a lens, which collects the sunlight on the paper. I did some calculation. This is also my hand, as you see. Then we have the sun. This is the viewing angle of the sun, and when we have, for example, a 3.5 centimeter focal length lens like this one, then we can calculate the size of the image. It is just a easy calculation. The image will be about 30 micrometer diameter. If we apply the equation for the intensity, we know that there are, when having this area, we have 0.7 watt intensity or power, dividing by this area, we get 1000 watts per centimeter square. So 1 kilowatt per centimeter square intensity is enough to light a paper. So let me calculate the intensity what we can reach with a laser. When we focus good quality laser, for example a Gaussian beam laser, or we can say that is TEM00 mode, then the intensity distribution can be explained by the Gaussian distribution, where we denote the W0, it is the radius at the beam waist. So if you have the cross-section of the intensity distribution, this is the place and it is the intensity, then the maximum intensity is decreased to 1 over ith value, then we can cross this intensity distribution, and its size has 2 W0, so it is the radius of the beam waist. There are also other beam waist definitions. When, for example, we speak about 1 over e square, it is a bit larger. So, but we will calculate then the power with this radius, and as the power or the intensity changes, we should integrate the intensity, which is dependent on the position, and this can be easily done. We get that the power will be 5 times the beam radius in the square, and multiply with the maximum intensity value. Thus we can calculate the intensity from this calculation. The intensity will be proportional, of course, with the laser power, what we can measure easily with the power meter, and we have to divide it by the pi and the radius of the beam waist square. Now we do this calculation, and we see the parameters of this simple experiment, where we have a power 0.15 watts. This is already a high power. You can have this even with continuous laser power, it is and 2 orders of magnitudes higher than, for example, this laser. The aperture of this laser is 1 millimeter. The focal length of this lens was 10 centimeters. Here we have the wavelength. We can calculate the spot size. The beam wave's radius was approximately 30 micrometers. So we can calculate the maximum intensity, which is 16.5 kilowatt divided by centimeter square. If you compare the focusing of sunshine and the focusing with laser, you see that the intensity of the laser light is 16 times higher than the focused sunlight. So with lasers, you can reach much higher intensities than with sunshine. So lasers can heat up materials very efficiently and initiate reactions, physical and chemical reactions. Let's see these physical and chemical reactions. When we have low intensity, just we heat up the surface. Then we can cause phase changes as melting, evaporation, and plasma formation. And if we are in vacuum, these things happen, and these things can be used to tailor the material surface, produce surface roughness, or produce holes, or even drill materials. And if we form plasma, this plasma can lead to another surface, and thin films can be grown. This is the basis of pulse laser deposition. The other thing is also quite interesting. When we just heat the surface or heat the gas phase above the surface, we can produce chemical reactions which can be oxidation and reduction, so redox reactions can be produced. When we melt materials, then the interdiffusion of atoms will be enhanced, so we can synthesize new materials. And when we have high temperature, we can produce etching, and even in unstable gas molecules, we can produce also deposition, which is not on the slide. And when we have very high plasma at the surface, then this gives new routes for chemistry. Using reactive plasmas, we have high intensity reactions, and even those materials can form compounds which do not like to do this at room temperature or at normal temperatures. So, turning to lasers, just remember the intensity definition. We have the energy divided by the area and time. How can we use lasers to produce material modifications? We need high intensity. What can we do? If we increase the energy of the laser, then we can reach high intensity, and such kind of lasers are the CO2 lasers, the carbon dioxide lasers. These lasers, by the nature, are continuous lasers, so the time is long, and if it is high, the intensity is reduced. But if we have high energy, then we can produce high intensity. And with this high intensity, we can just produce normal chemical reaction, burning the tree, and just moving the laser beam along this route, we can produce engraving. But if we have higher or stronger material like steel with some centimeters, we can cut steel with these type of lasers, because the energy content of the beam is really high. Of course, the laser drilling has some tricks, because usually an oxidizing gas, for example oxygen, is let into this nozzle, and not only the laser steps also for this laser cutting. With this technique, which is used in industry and also in automotive industry, maximum 3-4 centimeter thick steel can be cut with very precise and deep grooves. One interesting thing which carbon dioxide laser was used to drill glass. Glass is transparent, but glass is not transparent for carbon dioxide wavelength, which is 10.6 micrometer. The wavelength is 10.6 micrometer. So as the laser light absorbs in glass, nice holes can be drilled with carbon dioxide laser. The other possibility to increase the intensity then when we decrease the surface, as intensity is inversely proportional with the surface, and using a relatively low power laser at the ancient times that I worked with, it was a high power laser, 120 milliwatts. When we decrease the surface to some micrometers, we can evaporate the highest melting point material like tungsten. This is an atomic microscopic image in tungsten. But if we have some tungsten hexafluoride and hydrogen atmosphere above this surface, then the heat produces deposition of tungsten because the tungsten hexafluoride can be decomposed and tungsten remains on the surface. So even we can drill holes or deposit materials in a micrometer scale. The last possibility to increase power is to decrease the interaction time. Decreasing the interaction time is possible with pulse lasers, and if we keep the energy and keep the surface but decrease the time, then we can increase the power, and this is used for plasma formation. This is a pulse laser reaction chamber ablating the copper piece, and it has nice green color with plasma. And these lasers has very important roles also in dentistry. So if I want to give a summary on material processing by lasers, I can draw a table where on the x-axis we have the pulse duration, and at the y-axis we have the intensity. So having long duration and very high intensity lasers is difficult to make. You see here is a logarithmic scale, so here is 1 kilowatt, million kilowatt, billion kilowatts, billion watts, sorry, and this is terawatt and even higher powers. So to maintain a very high power laser for a long time is not possible, because just think about the power stations. The atomic power station power is a gigawatt. So kilo, mega, gigawatt. So we need to power such kind of laser with many atomic power stations. So practically we have no such laser, but when we use a material to excite, and this material stores the energy, and we use special switching methods for releasing this energy in a quick mode, then we can have high powers at that range. So, as I mentioned, decreasing the energy can increase the intensity, or when we have usually long time illumination, then the lasers are available at a certain low intensity increase the energy density of a laser pulse, let's say, and this is 10 millijoule. And this line shows that if we decrease the pulse duration, then the intensity will be increased, having the same energy density. And if we want to increase the energy density, then the 100 times we get the 1 joule over centimeter square, and 100 joule over centimeter square. Then we have this thing. In a given region with low intensities, we do not melt the material, so we get a solid phase. But above that region, the material will melt. If we use high intensity, it melts in a shorter time. But if we use a low intensity, we need larger time to melt the surface. This is a silicon material molten by a neodymium laser. If we increase the energy density and intensity, then we can vaporize the material and drill holes, and even increasing the energy density or using high power lasers, we can have the plasma. This is produced on a paper which was printed. You see the sign of our university, Szeged Tudományegyetem, University of Szeged, and this carbon deposit on the paper can be nicely evaporated by neodymium laser pulses. And at the highest intensities, you have multi-photon ionization, so more photons can be applied to reach a certain state, certain electronic state of the materials, and we get energetic plasmas, which are interesting for science, but in vaporization we can drill, cut, melting can be used for soldering, welding. Just remember the big robots which are doing the outer part of the cars in the factories, and heat treatment can lead to diffusion or recrystallization. I'm a material scientist, I like this figure, but I'm working at the Department of Dentistry, and we have to turn to the effects on living tissue. What happens with the living tissue? When using low intensities, even for a longer time, we have a soft laser therapy, which induces only some centigrade temperature increase. If we increase the intensity, then we heat up the material, which leads to coagulation of the cells or the protein, and at a very certain temperature, in temperature range, we can just use this laser effect for photodynamic therapy, which means that for example, cancerous cells are more sensitive to higher temperatures than normal cells, and with this temperature increase, we can selectively kill the cancerous cells. Oops. When we use evaporation, this can be used for laser surgery, and with a higher intensity, then we can evaporate hard tissues, which can be used for cavity preparation in teeth, for example. And then we use very high intensity plasmas. I think yesterday Katalin Hideki and another lecture was used of hadron therapy, so I will not talk about it. It's not my subject, but it's very interesting. So there is another thing which defines what we have with our surface. If I have a high intensity laser and a transparent material, then the effect will be negligible. So what we have to do to choose such kind of laser for a given material which is absorbs. So the absorption is also important when we want to compare the effects. So here is the random numbers PMU, and practically the absorption coefficient defines the range when we have high intensity in the material. So what I've introduced in my several papers, that usually people give energy of the laser pulses or energy density or intensity of the laser pulses, but these are not enough to know the effect. So we should know the intensity which is absorbed in the volume near to the surface, and to calculate this, when we have the normal intensity and multiply with the absorption coefficient, then we will have a kind of volumetric intensity, which is the effective intensity, and it describes the efficiency of the laser light itself. So when we just see this one, this is the definition of the intensity, energy divided by area and time. And if I rewrite alpha as 1 over alpha, we know that this is the absorption penetration depth. And absorption penetration depth multiplied with the area gives the volume. This shows then in what volume was the energy absorbed. And if the volume is small, then we have an efficient laser treatment, and if the volume is high, then the efficiency is decreasing. This was the physics which I like to talk about, but I will give some very basic definitions of teeth and their structure. I'm not the best person here because our next lecturer wrote already, but when we have teeth, we should speak about the part. This is the crown of the teeth. Here is near to the gingiva is the neck. What we don't see, that is the root of the teeth, and inside the roof we have the pulp, which contains blood vessels and nerves. Practically, this part of our body is a living organ. Even we don't think that this is living because it is very hard. Practically, the hardest tissue in our body are the having in the teeth. These are the upper or covering area. This is enamel, and inside we have the dentin, and here is the part cavity, and gingiva attaches to the lower part of the enamel, and the root of the teeth are covered with the cement, and teeth are embedded into the jaw bone. This is a healthy case, and what we want to speak about how the laser will interact with this tooth material. It is good to know what does a tooth contain. So I will speak about enamel. This is the outer part of the teeth, dentine and cement. What we have here, enamel consists 98% inorganic components, so it is practically very close to a normal materials processing, which we can do with lasers, and only 2% of organic materials. What we have, the most important thing is calcium phosphate. Calcium phosphate is similar to a ceramic material. It does not absorb light. If you look at your teeth and the edges of the teeth, it is slightly transparent. So So practically its absorption coefficient low in the visible light. The next constituent is dentine. It still has high percentage in inorganic components in the form of hydroxyapatite crystals, and the organic matrix is mostly collagen and proteoglycans, and has watering, and animal has water as well. And cementum layer covers the dentin of the root, and it has 50% inorganic materials. This is amorphous calcium phosphate and hydroxyapatite crystals, and it has high percentage from collagen fibers. So these materials usually the organic compounds are very strong ones and practically transparent crystals in the visible. The inner structure of the tooth, the dentine, you see such narrow gaps. These are the dentin tubules, and here's the interface of the pulp and dentin, and you see here cells. These are the odontoblast cells which help to grow the material of the dentine, and they are working a lifelong time. So the dentine will be thicker and thicker when years are passing. Unfortunately, the enamel, the outer part of our teeth, will be thinner and thinner. This causes that the color of dentine will appear sooner or later, which leads to appearance of yellower teeth. So it's a quite natural thing. We do not like this because we like nice white teeth, and many people use this teeth whitening. So the optical properties are important, as I mentioned. If we want to do something with lasers, we have to know the optical properties. This is the absorption spectrum of enamel in the visible range, and we see that it absorbs in the ultraviolet, and it is transparent in the long region of visible range. And in infrared, I found a transmission spectra which shows that when we have a low transmission, then we have a higher absorption. So here we have low transmission, high absorption, and we see that near to 3 micrometer we have an absorption line, and this is corresponding to the OH groups and the free water. Water absorbs light at 3 micrometer wavelength. And also we have a strong absorption line near to 9-10 micrometer, where we have the carbon dioxide laser. Let's see the dentine, and this is an absorption spectrum as well. As water content of dentine is high, it absorbs at 3 micrometer, and also phosphate parts and water absorbs at 9-10 micrometer, where carbon dioxide laser works. If you compare the absorption of dentine, cement, and enamel, we have similar curves. What we have, we see here that the highest absorption we have dentine and cementum, and the lower one is enamel. So the typical spectrum looks like this one, and the material which are consisting, which are the base of dentine, cement, and enamel are very similar. The inorganic content of the material is the highest in the enamel, so it has the lowest absorption to take into account that the animal is not very thick, especially when age is proceeds, then the animal will be thinner. And the last part of the tooth is the inner part, which has a very similar optical properties than the normal soft tissue. It mainly contains water, so here's the absorption spectrum of the water. And for example, blood contains hemoglobin, gives it a nice red color, which means it has higher absorption in the green. And also you see here the pigments absorption, which gives the absorption of our skin, or it can give the absorption of the soft tissues in the oral cavity. So, how can we use lasers in dentistry? We can have prevention, diagnosis, and therapy. For preventing purposes, we can treat the sensitivity of the lasers. We can supplement fluoride treatment and prevent tooth decay. That's quite an important thing, because prevention is always gives nicer result and gives a cheaper solution and more healthier solution. Not to have the illness is the best solution. But if we have illness, the therapy have to be applied. Therapy now it's a discussion, is teeth whitening is a therapy or not? I think it is. But tooth during root canal treatment, removal of the fillings, treatment of oral and periodontal diseases, laser surgery, photodynamic therapy, soft laser therapy, and many more are the task of the dentists. Let's start with carbon dioxide laser. Carbon dioxide laser is efficiently used as a laser knife because its wavelength efficiently absorbed in the soft tissues because soft tissues contains high amount of water. And we had an old professor in our faculty. His name is Zsolt Tóth, and he cured with lasers and also with cooling down cancerous tissues. So therapy, many thousands of people and make their life longer. He had some patient which he operated by lasers 30 or 40 years ago, and they have still contacts, and the patient is very healthy. Here we see some cancerous change at the lips, and the carbon dioxide laser treatment could be efficiently made. And you see here change at the lip, also close to the lips. And after the laser operation, you have a wound, and the wound after healing can be seen, but the cancerous lesions could be efficiently removed just by evaporating the cancer away. This is a very difficult job because how much to evaporate and what is the depth one should reach needs a lot of experience and a lot of knowledge. So what we have here, seeing this graph, then we have low power, then we have continuous laser, so long pulse duration, long interaction time, but high energy enough to evaporate the material. We can do the treatment at this American films, and everybody likes to be look like as an American actor. So the possibility is to treat these teeth by an oxidizing agent, which is usually hydrogen peroxide. There are also other agents, but the final result that hydrogen peroxide appears and penetrates into the teeth material and oxidizes those molecules, which gives the color of the teeth. We can enhance this process and illuminating this with a laser. You see, it is usually blue, strong lines, and due to enhanced reaction, then the curing takes less time. There are also only 3 aims of the patients when they go to a dentist. The first one, it should be quick. What do you think? What is the next one?
Without pain.
Without pain, yes. And what is the third one?
Cheap.
It should be no pain, cheap, and fast. And well, usually a professional tooth whitening takes an hour or even more. If we use lasers and we can enhance the speed with 2-3 time factors, then it gives a better result. Or if we get that 1 hour, then the result will be much nicer. So if you see the tooth whitening thing before and after, you see that 8-12 shades can be obtained with this laser treatment. The position of this type of illumination, you have long time and very little power, because you do not want to modify the teeth material.